All right, in today's lecture, we're going to finish the section 5.2 material on double integrals of functions over more general regions. So in these next couple of examples that we'll consider, we'll be looking at evaluating a double integral expressed in terms of an iterated integral, where we may have to reverse the order of integration in order to find an antiderivative. So as an example of this, in this next example, we're asked to evaluate the following iterated integral, and our inner integral is given with respect to x. So if I were to evaluate this, or try to evaluate this directly, I would have to find an antiderivative of e to the x squared with respect to x, which we can't do without making use of infinite series. So here, it's difficult to find an antiderivative of this function in the order dx dy, so let's see if we could try to reverse our order of integration. So let's start by considering the region that we're integrating over. So in this example, the region D of integration is the set of all points x, y, such that our y values are ranging from 0 to 1 when we look at our outer integral with respect to y, where we see that the values of y range from 0 to 1, and our inner integral with respect to x says that the values of x lie between 3y and 3. So the iterated integral is representing a double integral over a type 2 region. So let's see if we could express this as a type 1 region in order to reverse our order of integration. Now to do this, we could first sketch the region of integration. So in this example, in the xy plane, we're looking at the region D, where x is between 3y and 3. So if we were to solve this for y, we would have y is less than or equal to 1/3 x, so that would be the line passing through the origin with slope 1/3. Y equals x over 3, and x is bounded above or on the right by the line x equals 3. So we have our values of x are bounded to the left by this line, y equals x over 3, and to the right by the line y equals 3. And our values for y are bounded above and below by 0 and 1. So the region that we're talking about in this problem is the following shaded region. Now let's see if we can express this as a type 1 region. So another way to express this region D would be as the set of all points x, y, such that our x values range between the constants 0 and 3, and our values for y are bounded below by the x-axis, or y equals 0, and bounded above by this line x over 3. So this would be another way to express that same region. And to evaluate our iterated integral that we were given, where we first integrate e to the x squared with respect to x, and then with respect to y, we could evaluate instead in the order dy dx. So our outer integral would be with respect to x over the interval 0 to 3, And our inner integral with respect to y would be from 0 to x over 3. Here our function is e to the x squared, now in the order dy dx. So we first find an antiderivative of our function with respect to y. So we have the integral from 0 to 3 of e to the x squared power times y, evaluating from y equals 0 to x over 3, and then integrating with respect to x. So here, when we substitute x over 3 in place of y, we have a 1/3 integral from 0 to 3 of x e to the x squared. And then we subtract what we get when we plug in 0 for y, which would be 0. So here we just have 1/3 integral from 0 to 3, x e to the x squared power. And to evaluate this antiderivative, we would make use of a substitution. So if we let u be x squared, then du is equal to 2x dx. So we have for our integral a 1/6 integral of e to the u du. And let's change our limits of integration from x values to u values. So here, when x was equal to 0, we have u, which was x squared, would be 0. And when x is equal to 3, u, which is x squared, is 9. So then our antiderivative for this function is 1/6 e to the u power, and we're evaluating from 0 to 9. So we're left with a constant 1/6 times e to the 9th minus e to the 0, which is 1. So this would be the value of that given iterated integral. And in order to evaluate it, we had to reverse our order of integration and evaluate this thinking about D as a type 1 region instead of a type 2 region. So let's look at another example similar to this. In this next problem, we're asked to evaluate the iterated integral of x cubed sine of y cubed in the order dy dx. So again, in the order dy dx, we would first have to find an antiderivative of sine of y cubed with respect to y. And it's difficult to find an antiderivative of that function without making use of infinite series. So let's see if we could instead reverse the order of integration by thinking about our region D as type 2 instead of type 1. So in this example, our region of integration D is described as the set of all points x, y, such that our x values range between the constants 0 and 1, and our y values are bounded below by x squared and above by the constant 1. So let's visualize this region D. Here, our x values are ranging from 0 to 1, and our y values are bounded below by y equals x squared, so that is the parabola with vertex at the origin opening upward, and above by the constant y equals 1. That is the horizontal line passing through 1. So here we're looking at the shaded region D, and let's see if we could describe this as a type 2 region instead of a type 1 region. So here our curve, which is forming the right-hand boundary of our region D, is the curve y equals x squared, or solving for x. X is the square root of y, and it's being bounded on the left-hand edge by the constant x equals 0. And our y values are ranging between the constants 0 and 1. So another way to describe this region D would be as the set of all points xy such that y ranges from 0 to 1, and our x values are bounded on the left by the line x equals 0, and on the right by the curve x equals square root of y. So to evaluate our iterated integral that we were given in the order dy dx, we would reverse our order of integration, and we would be integrating for the outer integral with respect to y on the interval 0 to 1, and for our inner integral with respect to x from 0 to square root of y. Here our function is x cubed sine of y cubed dx dy. So now, evaluating the antiderivative of this function first with respect to x, we have the integral from 0 to 1 of 1/4 x to the 4th sine of y cubed, where we evaluate from x equals 0 to the square root of y, and then integrate with respect to y. So substituting the square root of y in place of x, we have the integral from 0 to 1 of 1/4 y squared times sine of y cubed, minus, when we plug in 0 for x, we get 0. So we've got the following integral. And to evaluate, again, we would make use of a substitution. So if we let u equal y cubed, then du is 3y squared dy. So our integral is then, let's see, we had a 1/4, and our y squared dy is going to be 1/3 of du, so we have 1/12, the integral of sine of u du. And again, let's change our y values to u values. So here, when y is equal to 0, u, which is y cubed, is also 0. And when y is equal to 1, u, which is y cubed, would be 1. So for our antiderivative, we have a negative 1/12 cosine of u evaluated from 0 to 1, which gives us a negative 1/12 cosine of 1 minus, when we substitute 0 in for u, we have a negative 1/12. Since we're subtracting that quantity, we have plus 1/12. Or if we want to simplify a little bit, we could factor out a 1/12, and we're left with 1 minus cosine of 1. So this would be the value of that iterated integral. And again, to get this value, we needed to consider our region of integration D is a type 2 region instead of a type 1 in order to find our antiderivative. Now, in the last part of this section, we will talk about some properties of double integrals, and then make use of some of these properties to evaluate, say, the average value of a function over a region, or try to estimate the value of a double integral if we're not able to find an antiderivative of our function. So this next theorem will describe some properties of double integrals, which we'll make use of throughout the remainder of the course. So in this theorem, we will consider two functions f and g, which are integrable functions over a bounded plane region D. So the first property is called the sum or difference rule, which says that the double integral of a sum or difference of two functions, f and g, over a region D is the same as the sum or difference of the double integrals of f and g evaluated individually. Our second property is the constant multiple rule, which says the double integral of a constant times a function over some region D is the same as the constant times the double integral of that function over the region D. So these rules really we've already been making use of when we're expressing these double integrals as iterated integrals. Now in our third part of this theorem, we're told that if the values of f are less than or equal to the values of g for every point xy in the region D, then the value of the double integral of our function f over that region D is less than or equal to the value of the double integral of g over that same region. In part 4 of this theorem, we have the following. If the region D can be expressed as the union of two regions, D1 and D2, which do not overlap except maybe on the boundaries of these regions, then to evaluate the double integral of the function f over that region, we could sum the value of the double integrals of f over the subregions D1 and D2 that made up our region D. So this seems maybe a little bit confusing at first, but let's try to interpret this visually. So if we had a region in the xy plane, which was the union of two subregions, say D1 and D2, which do not overlap, or perhaps they overlap but only on their boundaries. So maybe if we had some region D that could be split up into two parts, D1 and D2, where we maybe have some overlap on the boundary of these two regions. Then to evaluate the double integral over the union of those regions, we could evaluate the double integral over each individual region, say first over D1 and then over D2, and then sum those values to get the desired double integral. Now in the next part of our theorem, we are told that we can use double integrals to find the area of bounded plane regions. So the area of any plane region D can be evaluated as the double integral of the function 1 over that region D. So one way that we could think about this geometrically, let's recall that these double integrals can represent the volume of a solid that lies underneath the graph of some surface and above a plane region D. So let's say in the xy plane, we have some plane region D. If we evaluate the double integral of 1 over this region, we're thinking about finding the volume of the solid that lies below the plane, z equals 1, and above the region D. So we would be finding the volume of this little cylinder shape, whose cross sections are given by the area of D. So since the height of this cylinder would be 1 unit, the value for the volume of the cylinder would be the same as the area of this plane region D. Now in the last part of this theorem, we have the following. If our function f is bounded above and below by constants, let's say little m and capital M, for every value of xy in the region D, then the value of the double integral of our function over that region is bounded below by little m, that is the lower bound for our function, times the area of D, and it's bounded above by capital M, which was the upper bound for our function, times the area of the region D. So let's look at an example making use of some properties listed in this theorem. Here we are asked to estimate the value of the double integral of e to the x squared plus y squared over the region D, which is described to be the disk centered at the origin of radius 2. So in this example, let's start by sketching our region D. So here we were told our region is the disk centered at the origin of radius 2. So here everything inside of this circle centered at the origin of radius 2 would be our region of integration. Now, regardless of how we describe this as a type 1 or a type 2 region, it is difficult without the use of infinite series to find an antiderivative of e to the x squared plus y squared. So here, if we're just asked to estimate the value of this double integral, we can make use of our properties that we saw in the previous example. So let's think about trying to find an upper or lower bound on this function, e to the x squared plus y squared. So I know that on the disk, capital D, the value of x squared plus y squared is certainly non-negative, since the sum of squares must be at least 0, and the sum of the squares can't be any greater than 4 here, because the boundary of this disk is the circle centered at the origin of radius 2. That is, the circle x squared plus y squared is equal to 4. So the sum of the squares can be at most 4 for points in that disk. Now, to get our function e to the x squared plus y squared, we would need to exponentiate everything through this inequality. So on the left-hand side, I would have e to the 0 is less than or equal to the values of my function, e to the x squared plus y squared, which would be less than or equal to e to the 4th, or 1 is less than or equal to e to the x squared plus y squared, which is less than or equal to e to the 4th. So making use of the last part of the previous theorem, if I know the values of my function are bounded above and below by these constants, that means that the double integral of that function, e to the x squared plus y squared, over the region D, is bounded above by the constant e to the 4th times the area of our region D, and it is bounded below by the constant 1 times the area of the region D. So in the last part of this problem, we need to find the area of our region D, which in this case is a disk, or area inside of a circle. So the area inside a circle of radius r is given by pi times r squared. In this case, our radius was 2. So our area for this disk D is 4 pi. So substituting that into our inequality below, we have 4 pi is less than or equal to the double integral of e to the x squared plus y squared over the region D, which is bounded above by 4e to the fourth times pi. So we have an upper and lower bound for the value of the double integral that we're interested in. So here we're not able to calculate the exact value, but we can estimate the value of this integral by determining an upper and lower bound. We know that it lies somewhere between 4 pi and 4 pi times e to the fourth. Now in the last part of this section, we will talk about finding the average value of a function of two variables if we restrict ourselves to some bounded plane region D. So here we will define the average value of such a function. So if f is a function of two variables, which is integrable over some bounded plane region D that has an area given by a of D, then we define the average value of that function over the region D as 1 over the area of our region times the double integral of the function over that region D. So what we're doing is we're evaluating this double integral. So we're adding up the values of our function, f of xy, for every point xy in the region D. And then we're dividing by the area of D to calculate what we're defining as this average value. So in our last example, we are asked to find the average value of the function y minus x over the triangular region whose vertices are 0, 0, 0, 2, and 2, 2. So let's start by sketching this region. Here we're talking about a triangular region whose vertices are at the origin, 0, 0, at the point 0, 2, so 2 units above the origin, and at the point 2, 2. So we're looking at the shaded region shown here. Let's call this region D. So we know to calculate the average value of a function over this region D, we need to find its area. So below, let's compute the area of D, which is the area of a triangle. So here 1/2 base times height, and here both the height and the base of our triangle are 2. So we've got 1/2 times 2 squared, which leaves us with an area of 2 for that region. Now to find the average value of this function over our region, we're going to take 1 over the area of that region D times the double integral over D of our function, which was y minus x. So let's set this up. We have 1 over the area, which we found to be 2. So 1/2 of this double integral. And thinking about this region as a type 1 region, well, we see that our values of x lie between 0 and 2. So we could have our outer integral with respect to x from 0 to 2. And this region is bounded below by the line passing through the origin in the point 2, 2. That is the line y equals x. And it's bounded above by the horizontal line y equals 2. So our inner integral with respect to y would be the integral from x to 2, and our function is y minus x integrated in the order dy dx. So we have 1/2 the integral from 0 to 2 of our antiderivative with respect to y is 1/2 y squared minus x times y, evaluated from x to 2, and then integrating with respect to x. So we have 1/2 the integral from 0 to 2 of 4 over 2, or 2, minus 2x, and then we subtract what we get when we plug in x in place of y, which would be 1/2 x squared, and then minus a negative, so plus x squared, integrated with respect to x. So we're left with a 1/2 integral from 0 to 2 of 2 minus 2x plus 1/2 x squared with respect to x, which gives us 1/2 of, for our antiderivative, we have 2x minus x squared plus 1 over 6x cubed, evaluated from 0 to 2. So substituting 2 for x, we have 1/2 of 4 minus 4 plus 8 over 6, or 4/3. And then we subtract what we get when we plug in 0, which is just 0. So we're left with 1/2 of 4/3, or 2/3, for the average value of this function over that triangular region D.